The two types of systems that we've seen so far are series systems and parallel systems. We now present something called a K out of N system, and a K out of N system generalizes a series system and a parallel system. So here's the definition. A K out of N system functions if and only if K or more out of its N components function. The word function at the end of that definition could have been failed, so you have really two different types of K out of N systems. So let me go ahead and write two that you will see in the literature. One is K out of N, and then they tend to put a colon here, and they will either put a capital G or they'll put a colon and then they'll have a capital F. G for good, F for failed. So when you see the definition in this form right here, that's really the same as saying a K out of N G, G for good, system. How does a K out of N system relate to the ones we already have seen, which are series and parallel? Well, a series system is just an N out of N system, which says all N of the components have to function. A parallel system is at the other extreme, and that's just a 1 out of N system. That is to say, if one or more of the N components function, then the system is functioning. Here are a couple examples. A suspension bridge that requires only K of its N cables is a K out of N system. An automobile engine that requires only K of its N cylinders to turn over is a K out of N system. A bicycle wheel that requires only K out of its N spokes is a K out of N system. When a dog gets an injured paw or the like, oftentimes they can adapt and they are able to run or walk on 3 of their 4 legs. That's an example of a 3 out of 4 system. Anytime you have a team sport, for example, if a basketball team is 12 players, then to keep 5 people on the court for injuries or the like, they are basically a 5 out of 12 system to have a full 5 on the court. So the structure function for a K out of N system is phi of x is 1 if, and then there's this summation right here. What that is doing is it's adding up the number of functioning components, right? Because these xi's are zeros or ones, 0 for failed, 1 for functioning. So when you add up all those xi's, that tells you how many of those components are functioning. And if that happens to be greater than or equal to K, then the system is up. If it happens to be less than K, then the system has failed. There are two types of systems which are not K out of N systems but are very close. The first one is called a consecutive K out of N system. This type of system depends on where those K failures occur. And for example, if a bicycle spoke fails and the wheel is still operating, if another spoke is to fail, you don't want it to be the spoke right next to the failed one because that's a weaker tire. You want it to be in another spot on the tire. So consecutive K out of N systems consider where the particular failures occur. Second one is a circular K out of N system, and the bicycle wheel example also applies to that. That's where you're looking at things circularly, and you can have both circular and consecutive K out of N systems. So there are a number of spin-offs to the K out of N system that you see here. Finally, this last sentence down here at the bottom, block diagrams for a K out of N system require repeated components, and that's going to be illustrated on the next slide, where we look at a 2 out of 3 system. Now the thing to remember is when you have a 2 out of 3 system, there are really only 3 components in the system. Components 1, 2, and 3. However, in order to write this as a reliability block diagram, you have to use repeated components. So this is a block diagram that describes a 2 out of 3 system. Notice if 1 and 2 are functioning, then the system functions. If 1 and 3 function, then you have 2 out of 3 functioning. Or if you have 2 out of 3, 2 and 3 functioning, then the system is functioning. And that's the appropriate block diagram for a 2 out of 3 system. Once it's written, or I should say drawn in this fashion, then it's pretty easy to write down the structure function. This is at its essence a parallel system of 3 two-component subsystems. So the structure function will be 1 minus the product of 1 minus x1, x2, because x1 and x2 are in series, 1 minus x1, x3, because components 1 and 3 are in series, and 1 minus x2, x3, because 2 and 3 are in series. If you feel like multiplying this out, you will get this expression right here. So that is an example of a 2 out of 3 system. Now this can sometimes come up on what's called a voting system. These can occur, for example, on a fly-by-wire aircraft in which basically if an action is given from the pilot to do a particular function on the aircraft, you might have 2 or 3 different ways of looking at that. And if you have, let's say, 3 different ways to do a particular command that the pilot initiates, then if 2 or more of those agree, then you'll take what the 2 out of 3 tell you to do. And that's one way that a voting system works. Here's an example of a non-K out of N system. An airplane has 4 propellers, 2 on each wing. The airplane will fly if at least one propeller on each wing functions. Find the structure function phi of x. So this is going to be the fuselage right here. Here's the right wing. Here's the rest of the fuselage. Here's the left wing. The aircraft is headed in this direction, which means propellers 1 and 2 are on the left wing. That's this. Propellers 3 and 4 are on the right wing. The wings are basically a series system here. And the only thing we're considering are the propellers. We're not considering other parts of the aircraft. So if each wing is a 2-component parallel subsystem of propellers, then what you have is you have a parallel subsystem for propellers 1 and 2. You have another parallel subsystem for propellers 3 and 4. Those are arranged in series. And the structure function phi here will be one system multiplied by another subsystem. Both of those subsystems are parallel, so you have 1 minus x1, y minus x2, and in the second subsystem you have 1 minus x3, 1 minus x4. And that's how you draw a reliability block diagram and figure out a structure function in a slightly more complicated system. This system right here is not a K out of N system. Here's an exercise. Find the structure function phi of x for the system below. So there is a 3-component system, and we want to do the structure function 2 ways. We want to do it in terms of minimums and maximums, and also we want to do this algebraically. So let's start out with the algebraic version of this. We say phi of x, And I could write out the components here. It's really x1, x2, x3. Or you could also have put x and put it in boldface or drawn a line over it. And so the first component is x1, and because it's in series with this subsystem, it will get multiplied by the structure function for a two-component parallel system, which is 1 minus x2, 1 minus x3, and that's it. You could multiply that out if you wanted to, but leaving it that way is fine as well. Now that's doing it algebraically. Now what we're going to do is we're going to do it in terms of mins and maxes. Now keep in mind, I could write out x1, x2, x3 here, and I've got a couple other options. I could have put an x in boldface for x1, x2, x3. I could put an x with a line over or an arrow over it, or I could put an x with a line under it. Any of those are fine for writing a vector. We'll go x with a line under it, but just keep in mind that that means x1, x2, x3. The system is again a series system. So because of that, when we're using mins and maxes, if you remember from before, a series system has a minimum out front. And so this is going to be the minimum of the first component. That's x1. And then what you have is you have a second component. And that second component is a parallel subsystem. So you will have the maximum of x2 and x3. And there's the structure function written as mins and maxes. Another example here is something known as a bridge structure. This does not occur a lot in practice, but it's a slightly more complicated system. And here is the block diagram for a 5-component bridge structure. If you think about paths that go through the system, components 1, 3, and 5, if you want to start on the left and draw through functioning components and make it to the right, 1, 3, and 5 will get you there. That's a path through 1, then down through 3, then across through 5. Also, the path 1 and 4 will get you from the left to the right. 2, 3, and 4 will also get you from the left to the right. And finally, 2 and 5, if you pass through 2 and 5 and they're both operating, that will get you from the left to the right. A little bit later, these 4 sets of components we have written here are going to be something called a minimal path set, but we won't look into that right now. But based on those paths through the system, we can draw an alternative block diagram for that bridge system that looks like this. It's ultimately a parallel system with series subsystems, and notice the 1, 3, 5, the 1, 4, the 2, 3, 4, and the 2, 5 are the elements in each of those systems. So from this alternative block diagram, we can write down what phi of x is. And I'm not going to write out x1, x2, x3, x4, x5. I'll just call that the vector x. Keep in mind that this is a parallel system, so we start with a 1 minus, and then what we do is we put in 1 minus, and we look at that first subsystem. That's x1, x3, and x5, and that gets multiplied by the next subsystem, which is 1 minus x1, x4. That gets multiplied by the next subsystem, which is x2, x3, x4. These are being multiplied because they are series systems. And then the last one here, running out of room, is 1 minus x2, x5. And that is the structure function for a bridge system.